Right. So we went on to explore, um, to step into each uh, basic function that we looked at before, and look at how various parameters affect the graph of a function in that family. So we started out with, well, this is from last year in grade 9, um, basic function y is equal to x, which we saw results in a straight line graph. And so what we're interested in is what happens when I change this number. So if instead of y is equal to 1x or y is equal to x, I have y is equal to 2x, y is equal to 10x, y is equal to a half x, y is equal to negative 5x. How are the corresponding graphs going to look? And it's important to realize that all of those functions are fundamentally related to this guy, y is equal to x. Because if I now think about, so I'm just going to keep this guy here, y is equal to x, the graph of y is equal to x, as a point of reference for us. If I think about the graph of y is equal to 2x, all that's happening there is, formally, when my input was 1, my output was 1, y is equal to x. Now we're saying y is equal to 2 times x. So when my input is 1, my output is going to be double this. So it's going to be, we can plot a point there, it's going to be up here. And over here, where my input was 2 and my output was 2, now when my input is 2, my output is going to be double that former output. So my output is going to be over there, right? And if we look at 0, for example, that's not going to be affected because an output of 0 times by 2 is still just going to be 0. So we're going to put a point there. And then formally, when my input was -1, my output was -1, but now that is going to be doubled because we're multiplying the output by 2. So that output is going to be over there, and so it goes. So you end up with a straight line that is a bit steeper than the previous one, y is equal to x. And similarly, you can reason about what the graph of y is equal to 3 to the x would look like, right? So if you were to change that to a 3, that would just mean that all your outputs are being multiplied by 3. Some of this is off the screen, so we can't see. So you end up with an even steeper graph. Let me just hide these points that we made in the meantime. So you would end up with a graph that does that. So where my output was formerly just 1, it's now going to be 3 times that. It's going to be 3. Where my output was formerly -1, we're tripling that, so it's going to be -3. And so it goes. The higher A becomes, the steeper your graph becomes. And that's what we learned when we learned about straight lines. Y is equal to mx plus c. M represents the gradient of the line. And that's because the output is being multiplied by that factor. The output on your original y is equal to x line is being multiplied by that factor. So you don't just have a 1-1 situation anymore. Over here, you're going to have a 1-7 situation and a 2-14 situation. So your graph ends up being very steep, and so it goes, right? And then what happens if this number is a proper fraction? So something between 0 and 1. Right, so again, we go back to our basic shape, y is equal to x, looking like that. If I were to change that, the number multiplying x to a proper fraction, like 0.75 or 3/4, okay, so what's happening now is that where my output was formerly 1, we are multiplying that by 3/4, so it ends up being a bit smaller. Where my output was previously 2, we take 3/4 of 2, which is 1.5, so your output ends up being over there. Where your output was formerly 3, again, you take 3/4 of that and end up with a number that's over there. So overall, you end up with a graph that's not as steep, that's less steep than before. And you'll see that if we're to decrease that even more, we're decreasing the gradient effectively. So when my output was formerly 2, my output is now 1. right? When my input is 2, I'm going to have half of 2, which is 1, and so on. So decreasing this number over here decreases the gradient because it's decreasing the outputs, so to say. Well, I mean, depending on which side you're looking. So if you look on this side, on the negative side, it's actually increasing the outputs, right? So if you take a quarter of -1, that's going to be a much less negative output than that guy over there, right? Or if you take a quarter of -2, then you end up with -1/2, as opposed to the original -2. And so it goes. So that's the effect of that number over there. It messes with the gradient of the line. And the final case to consider is what happens when that number is negative. So there's our original shape again. And when we make this number negative, what happens is that our outputs get flipped, right? So where my output was originally +1, we're saying -1 times that original output, so it comes over here. -1 times this output, so it comes over here. -1 times that output does that, and on this side, originally in the y is equal to x shape, when my input was -1, my output was -1, but now we're saying y is equal to -1 times x, so take this output and times it by -1. Take that guy, times it by -1, so you end up with positive output. So overall, what that ends up doing is flipping the line around, reflecting it in the y-axis effectively, or in the x-axis, however you want to look at it. But the idea is that this line now has a gradient that goes this way as opposed to that way. And if you're to make it more and more negative, then you just end up with a steep line that goes in this direction. So that's the effect of this number on the function y is equal to ax. So to say it, it's very similar for the other functions as well. So there's our basic parabola, y is equal to x squared. If I'm to change that to y is equal to 2x squared, so there's the original y is equal to x squared, what's happening is that we're doubling all of that original parabola's output. So where my output was previously 1, we're timesing that by 2 to get an output of 2. So we're saying that, okay, what's the output of y is equal to x squared? And then times that by 2. So you get 2 instead of 1. Over here, where your output was previously 4, now your output is going to be twice that. It's going to be 8, and so it goes. Where your output was originally 9, it's now going to be way up. It's going to be 18, and the same is happening on the other side over here. And of course, this point is unaffected because the output in the original parabola, when my input is 0, 0 squared is 0, and if you times that by 2, it's still 0. So that stays the same. But the other guys, their outputs get doubled. Well, I mean, I suppose this one was also doubled. It just didn't change in value. So all in all, that makes your parabola narrower because your outputs are a lot bigger, a lot more quickly. And so it goes. So if you're to change that to a 3, but becomes even narrower because again now your original outputs are being multiplied by 3. If we change that to a 4, even narrower. Change that to a 5, even narrower. So that's one of the effects of this number on the shape of your parabola. If it's a big number, then it's going to make your graph narrower and narrower. And if it's a proper fraction, so something between 0 and 1, you're ending up with graphs that aren't as steep. So for instance, if we're back at our original parabola, y is equal to x squared, and we say y is equal to 0.75 x squared, so 3/4 of x squared. What we're saying is take the output of the original parabola and multiply it by 3/4. So you're going to get a smaller number than before for each of the outputs. So over here, my original output was 1, and now it's going to be 3/4 of that. Where my original output was 4, it's now going to be 3/4 of that. It's going to be 3. So you end up with a graph that is slightly flatter. And if you're to change that to a half, then it becomes even flatter because you're taking an even smaller portion of the original output. And if you make it 0.25 or a quarter, then it's even smaller. So where my output was originally 1, it's now all the way down here at a quarter. Where it was originally 4, it's now 1 because a quarter of 4 is 1. And now we can even see the output when the input is 3. So originally, on my original parabola, y is equal to 3 squared is 9, but now we're saying take that 9 multiplied with a quarter, so you end up with 2 and a quarter over there. Likewise with 4, when my input is 4, in the original parabola, y is equal to x squared, you get the output of 16, but now we're saying take a quarter of that output, so you end up with an output of 4. So that's how you end up with a flatter graph than before. And the same happens with your parabolas and your exponential graphs as well. Let's just quickly look at that. So take our hyperbola, for instance. If we're to play around with this number over here, then you end up with, say if you have y is equal to 2 over x, just remember that y is equal to 2 over x is just the same as, so let's just clear this quickly. It's the same as 2 times 1 over x. And if you're not convinced by that, maybe pause the video and have a look. Work this out, see if you don't come back to 2 over x. So all that's happening there is that we're taking all the outputs of our original hyperbola, y is equal to 1 over x, and multiplying those outputs by 2. So that's what you're seeing over here, where my output was previously -1, it's now -2. Where it was over here, it's now over here. So everything is just multiplied by a factor of 2. Likewise on this side, all my outputs are being doubled to produce this new hyperbola. And so the higher this number goes, the steeper the graph becomes, because in this case the outputs are being tripled. And so it goes. But this doesn't affect the asymptotes, as we'll see if we move this way, because ultimately the numbers just all become very small. Y is equal to 1 over x, y is equal to 3 over x. Once the input is big enough, then y is equal to 3 over x is also going to become very, very small and approach 0. And if you have a fraction as this parameter, a proper fraction, so say you have 0.75, you aren't commonly going to see it looking like this. This is where it's important to go back to this little fact that we discussed over here, that y is equal to 0.75 over x is the same as y is equal to 0.75 times 1 over x, which is the same as 3/4 times 1 over x. And so the way that you'll commonly see it is you'll see it looking like this. So that's still a hyperbola in disguise. It's 3/4 times 1 over x, which means that I'm taking all the outputs of my original hyperbola 1 over x, y is equal to 1 over x, and timesing them by 3/4. So you end up with a graph that's not as steep as before, because we're taking 3/4 of the original outputs. And so the smaller you make this number, the less steep that graph is going to be. And the same applies to your exponential graphs. So this is a basic exponential graph where all that's happening is you're saying y is equal to 2 to the x. The 1 times 2 to the x doesn't really do much to the output, right? Doesn't affect it. If you're to change that to a 2 times 2 to the x, then what you're saying is take all the original output of my y is equal to 2 to the x and double it. So where my output was 1, it's now 2. Where my output was 4, it's now going to be all the way up there at 8. And so it goes, when you make the number even higher, then you end up with an even steeper graph, because you're multiplying all your outputs by that factor. And if you're to make this a fraction, then you would end up with a less steep graph, as you see here.